Hello everybody and thanks for tuning in. You are on the online course Easy Geosteering. In this course we explore the key geosteering aspects in simple terms, following a clear and structured approach. We are currently in the first part of the course, Necessary Theory, and in the previous video we gave the definition of geosteering and outlined main geological tasks and geosteering tools. And today we explore the challenges that make our work more complex, key uncertainties and lateral changes. Let's get started. So, what prevents us from performing geological tasks? We call it key uncertainties. We will list 6 points and you may come across 1 or 2 of them or even more at once. Some of them are caused by insufficient accuracy of geological model and structure map, while others are caused by drilling technology and human factor. The first one, TVDSS uncertainty. For example, according to the structure map, you expect to enter target layer at certain TVD. But in fact, after real-time data analysis, you realize that your target layer is positioned higher than expected. If you continue drilling according to the plan, you will drill through layer and come to bottom. It means that we need to raise T1 point and be careful with DLS, we must not exceed it. In good cases, we raise T1 by 3-5 meters. In more challenging situations, it's about 5-10 meters and even more. The second point is deep uncertainty. For example, initial structure map shows us subhorizontal surface, but in real time we observe deepen up. Again, we raise T1 point taking into consideration DLS limitations. Or if you see deepen down, you need to lower T1 point, it's always easier. Point number 3, faults. Faults are fractures in the earth crust where rock layers have shifted due to tectonic movements or local stresses. They can be normal or reverse, with displacement ranging from a few meters to several dozen. Identifying faults in real time is often challenging, and their presence makes it harder to determine the borehole's position relative to the geological section. Number 4. Varying reservoir properties in the target layer. For example, we might expect equally good properties throughout the entire formation and plan to drill in the top section. However, in real time we're observing that the clay content is higher than expected in this zone, which reduces the quality of the reservoir. We can change the trajectory and try to find better properties in the bottom section. Number 5. Distance from MLWD sensor to the bit. The drilling BHA typically includes the bit, a mud motor or rotary steerable system, and only then LWD tools. Every sensor has its own distance to the bit. The worst case scenario is about 30 meters for neutron density. The best one is about 2 meters for rotary steerable system gamma ray. But the fact is, we always have blind zone. We can still see the productive layer by sensors, while the bit is already 15 meters deep in non-reservoir. And point number 6, accuracy of MD, inclination and azimuth measurements. As mentioned in video number 1, we physically measure only these 3 parameters in the survey report, while the others are calculated. If we make an error in MD, it will affect TVD and TVDSS. This is critically important when drilling close to the oil-water contact, for example. If we drill using only gamma ray, we may not even notice when we cross the water level, because, as we will see later, gamma ray cannot distinguish between oil and water saturation. Alright, we outlined 6 key uncertainties, and now we come to perhaps the most challenging factor to handle, lateral changes in the formation. Let's take a closer look in the next slides. Lateral changes refer to lithology variations within the target layer and changes in formation thickness along a certain drilling azimuth. At first, let's see how the cross-section looks when there are no lateral changes. At this picture we have a target formation with a continuous shale layer inside. Continuous means that this layer doesn't break along the well, and we can observe it with the same thickness in the offset wells. But if we have lateral changes, the shale layer, for example, might change its thickness or even break. In this example, it disappears entirely after point B. and we will no longer encounter it along the current azimuth. Instead, we might observe some local geological bodies which may not exist in other wells. The most critical issue here is that we might confuse a local geological body near the bottom with our shale layer near the top, leading to incorrect recommendations for further drilling. And finally, the thickness of the target layer itself may decrease. We also call it pinching out of the layer. So, we have covered lateral changes on the cross-section, and now let's take a look at them from the plan view. Okay, let's imagine that we need to drill in the edge reservoir area. According to the geological model, everything appears fine, and we plan to drill parallel to the bed boundary in the northeast direction. However, at point 1 we exit the productive zone, and not because we crossed the top or bottom of the target, but due to lateral changes. Non-reservoir came from the side rather than from above or below. In most cases, there is little we can do in such situations. We either finish drilling the well or block up the carriage and wait for the reservoir to return at point 2. Okay, all of mentioned points constitute lateral changes and complicate the geosteering process. Just imagine that your deposit has faults, local geological bodies, thin and non-continuous target layer with different properties, and you're responsible to drill inside the reservoir using just one gamma ray sensor in 15 meters from the bit. Sounds challenging, right? But it's our real job, and some type of lateral changes to some extent is always observed during the geosteering process. But it's not all doom and gloom. We do have things that help us manage these challenges. So, how do we deal with key uncertainties? Here is one rule that works anytime and anywhere. To complete geological tasks, we need to use all available information. What types of data do we have during the geosteering process? First of all, the geological project. This is the main document containing all the necessary initial information about a specific well. Next, MLWD data. Real-time logging curves and surveys are our eyes and ears on the ground. We use them to estimate the formation properties and figure out whether we're inside the target layer or not. Point number 3, geosteering methods and tools. We use them to define the wellbore position on the cross-section and to form recommendation for further drilling. Additionally, some projects benefit from other sources of information. For example, drilled cuttings can sometimes clearly indicate if we are inside the reservoir or not. Occasionally, ROP also shows a strong correlation with the reservoir flag. And if you have petrophysical or geomechanical services available in real time, that's even better. Use them to help answer the critical question, where we are. Alright, we outlined the 6 main uncertainties for geosteering and found out what the lateral changes are. Hope you like this video. Don't forget you can enhance your practical skills with the private lessons. We will use modern tools and drilling simulators in StarSteer to give you an immersive experience as a true geosteering engineer. Stay tuned and give this video a thumbs up. In the next lesson, we will explore what the geological project is and dive into drilling and landing strategies. See you then. Bye-bye.